Welcome everyone to the third lecture in the series. It's a pleasure again to have you.
All right, so yeah, pleasure to be here for this last lecture. So actually the plan will be a bit strange. So I try to take the story that we built on in the first two lectures and take it to a conclusion and summarize the results we get from this method. And actually, I also want to discuss, like, there's really two aspects here. I've been focusing on what we can learn about infrared modifications of gravity, assuming some consistency at all energies. But I think in addition to this sort of abstract principle, abstract constraint, it's nice to just study what actually happens in models. So to ground our intuition. So I want to discuss a little bit something we observed in UV completions, and that led to some conjectures about that guide us about the next step. So what can actually happen if it's high energy scales where I described yesterday, this I spin 4 particles and I spin particles start to kick in. So I want to discuss this. So all of this will be taking place in empty AdS, or more precisely, a locally flat region of it. And then I also want to discuss some other thing, which I think is a bit a separate topic, but it's a fun thing. Is just to ask, suppose you actually had an holographic system, and that was not empty AdS, and you wanted to probe the geometry of it. What would you do experimentally? So I want to discuss this stuff. So I would probably skip some of these things just to get to the see how it goes. Feedback is always hidden. So okay. So this is actually most of the first few slides I've already described. So yeah, in empty AdS, that was our starting point. The nodular can cut through the same amount of time it goes to the bulk. And the CFT gives this very exact statement that these two measurements of the boundary commute on this baseline. And this means that in the bulk, you cannot have faster than light. And that turned into CFT bootstrap. When we take the matrix element of this statement, scattering state, this gives the bootstrap equation, and we manipulated it to get something like the S matrix dispersion. Let's discuss this. So we get this type of sum rules, which are things you can calculate at low energy to sum over processes that happen at high energies. And this picture here is meant to use basically yesterday where the formula that has the imaginary part of scattering amplitude. Basically here to draw it like this, I use the optical theorem to write this as the amplitude scoring. So that's why it's fun. So sum over processes that happen in high energy. And the special thing about gravity, which we did not get last time, is that the tree-level amplitude grows like S squared. And these techniques allow us to constrain anything which grows like S squared. So we cannot constrain things that do not grow. Or photon exchange, not constrained. The lambda phi 4, not constrained. Anything that goes like S squared, like G Newton, S squared with C, that we get from the diagram, we can constrain. And then we get a sum rule for G Newton. Some positive unknowns.
Sorry, just meaning during towards the end of yesterday's discussion, I was not very clear that at tree level it's the S squared.
Yes.
That is the bound, especially at fixed T. Right. I mean, in the wave packet language, you did that derivation. Right?
Yes. Exactly.
But in the fixed T language, it seemed like you get one factor as more.
Yeah.
So why is it not S cubed?
It still means to be in this wave packet language.
Okay.
So this integral will become some G Newton times S squared times. This wave packet you can think of as being focused on some impact parameter B. And that would give something like 150 minus 4. So this is G Newton. And in fact, here this is not drawn in this schematic equation.
In gravity, it is S squared fixed.
Instant gravity, yes.
Just is.
It is, yes.
Yeah.
No, but
I think
if you want to constrain, then maybe some rules, etc., that you want to use arc of fusion.
Yeah.
For that, I mean, you want to use a priori set about that, right? Out of that.
So first, I think he's going to divide by S cube and take a dispersion relation. So he's going to pick out the part that is S squared and low energy.
Yeah. So we took yes over extreme.
So
If that will work, if the growth is like S square, the expected growth is like is supposed
less than S squared.
yeah, less than S square, right? But
Yeah.
that was not clear. Less than equal to S square. That was not clear. Right?
Oh, yeah, we're using the
Actually,
same.
fixed T was not clear.
Yeah, but we're not really doing fixed T. More like. But one important thing is that's related is that we get actually infinitely many some rules. Because you can measure G Newton using scattering at different parameters. Very far, very small. We actually get infinitely many some rule at this time. So, and as you get to shorter distances, you will not probe just G Newton, you probe also G Newton and corrections.
But I thought in string theory, this S to the power 2 plus alpha prime T is sharp.
Yeah, in P space it's true. But we don't have to
No, I
use
mean,
that.
even in fixed T, right?
Yeah.
It's true. Yeah.
Yeah.
Yeah, so string theory is something stronger than what I would use.
I see. So this does not quite. I mean, if in string theory it was 3 plus alpha prime S
Then this will
alpha
not-
prime T, it would not work. But
But this is not allowed.
I don't think it. Yeah, I mean, you're saying there's a weaker bound in T. I don't think that's true.
that's what
I don't think it's true.
I mean, we
I think
should.
I'm misunderstanding these two, but
Okay.
but it was never.
See, what I want is like a bound on classical scattering at fixed T. What would you say that is?
I think it's complicated and it depends on the space-time dimension.
It's not S squared.
No, sometimes it's worse than S square. But it's discussed in the algebraic and area, but it depends a lot on the transverse growth.
Even with the classical limit.
Yeah.
Yeah, so this is a
Quite a pole,
it's
just pole exchange. Just pole. I mean, this Gibber whatever talks about icons and so on.
Exactly.
And just talk about one pole.
Exactly. So
no, there is no issue in the B integration. I think.
No, I mean just this business.
no, but in order to understand the true behavior of this M at truly large S, we do need to.
No, but
classical.
classical level.
But this is
Classical in the sense that in the sense of just a single exchange. Then there shouldn't be any problem.
Yeah, but
It's three
let me draw the
It's three level. I think
Right.
that's
So there's some range. So for some B that's fixed, there's some range here that this 3 level works here, and then there's some range of high energies where you need to resolve. And what we're really using in this in order to make these arguments, the arguments are not we need the true behavior of the decomposition to vanish faster than that. With this using the true behavior in the UV, including all these ladders and everything.
And everything like that, whatever it takes.
Yeah, exactly.
Yeah.
So a starting point is not a statement about the tree level exchange. The tree level exchange actually violates the bound. That's okay.
Right. No, but while it's with what?
It's just S squared.
S squared.
It
Right?
violates-
It's not less than S squared.
That's square. It's squared.
Yeah.
Cannot be greater than S squared.
Yeah. So this bound of chaos that constrained it.
Yeah.
But that's unrelated to that.
Yeah, it's unrelated, but
Yeah.
it follows from that, right?
Exactly. From this you prove the bound of chaos, which implies it cannot go faster.
Yeah, now I'm just wondering whether that B integration will spoil the 1 over N piece also. I mean, when you move to T language.
We'll spoil the one. We'll spoil one.
The 1 over N, I mean, the that piece, that one single exchange.
Yes. No, I think it makes it better because if you choose B to be larger, it's
Because I don't quite know, right? I mean, I just know that it goes like 1 over N squared. It could be some very complicated what that is a meromorphic scattering amplitude, right?
Yeah.
So meromorphic scattering amplitude can have an entire function piece.
no, but okay.
And how do I know that how it goes?
You don't have to assume it's neuromorphic. So this contour deformation, we're thinking of doing this below. We only evaluating below the string state. So this regime that you asked, that we discussed about S alpha prime P, this is for S or P plus alpha prime P. This regime is for S bigger than MS squared. We're not operating in this regime. We're operating in the regime where it's still below the string scale. So that's why we can definitely trust this 3-level extent on the left. But we assume that as you increase the energy, this bound is satisfied. This bound can be satisfied in various ways. One of them is because of this alpha prime T correction. Another of them is because of this ladder resonation. There are many mechanisms to satisfy this, but we don't need to know what mechanism. We just need to know that it happens.
Yeah, no, I was just concerning myself with the expansion when you do have
Yes.
a 1/n square parameter.
Yeah.
And then the question is, what can we say about that piece?
Yeah.
And that's the only question that let's say I'm looking at first.
Yeah.
Right?
Yeah. Okay, I understand. I will come to that. So you're asking, how do we know that the loops are small? That's the one we're looking.
No, I mean you could have, some sort of a classical interaction, tree-level interaction.
Yeah.
Not necessarily loops, let's say, just tree-level,
Yeah.
tree-level classical interaction.
Yeah.
But it could have many derivatives, right? So that the amplitude is still, classical in the sense of being meromorphic.
Yeah.
And then how do I know that the behavior at large impact parameters such that I can just ignore that contribution?
Anything larger than S squared will violate the chaos bound when put in.
So if you put a lot of, the picture here is that if you put a lot of derivatives,
I mean,
And it doesn't-
able to change in the impact parameter versus fixed T.
yeah, but if you put more derivatives, it will decay
chaos
faster. So it's going the other way. If you put more derivatives, it will decay faster at large.
Yeah.
The way we bound the derivatives by going to smaller.
No, I mean, what I'm saying is that you can have infinitely many derivatives which can reach to something.
Well, that's exchange of a different, that would be exchange of a like particle. So we discuss one thing something that tangentially address your comment is, how do we know that, for example, that two gravitons can exchange scale or type of like particles? So you actually get a bound on this comments. Yeah, so general object is okay, you get these some rules for G Newton. They do two things for you. One of them is they show that G Newton gravity is attractive. Great. Okay. This made us very happy.
Positivity.
Yeah.
Translates
Three
to
of this implies attractiveness of gravity. It was known by Newton. Still made us very happy. But the other thing that this does is that this gives you a budget. It tells you that the heavy states cannot couple too strongly to two gravitons. Otherwise, you max out your budget that you can measure.
Otherwise, you max out your budget for what?
So G Newton, yeah. G Newton is something you measure in the infrared.
Okay, knowing what G Newton is, you get
Exactly. So knowing that G Newton is small and some units tells you that the states that the graviton couple to the graviton has to couple weakly to anything. Okay. So already just from that some rule we exclude if G Newton is small, so basically this whole thing exclude any strong coupling of graviton to anything below the Planck scale.
What is the statement at that figure?
The statement.
The first equation you showed in the terms of Feynman. The first
Just the equation.
Yeah. What is the statement there? What you want to say from that view?
It's a dispersion relation by divided by x cubed.
Yeah, it's that dispersion relation that we discussed.
But then it will be positive for any theory, right?
We positive for any yes.
Any theory. So
For any what?
for any theory, this
Yeah.
right hand side will be
Yeah.
positive.
Right.
So it will be attractive for any theory.
There's no theory of gravity with gravity is equal.
No, not I am talking about the right. Any theory, any quantum theory will be positive.
Yeah, exactly. You could make so these arguments say you always this positive sums.
Yeah.
But typically the left hand side of this sum will be some integral of that I erase here of ds over x cubed what they are.
Divided by x cubed. You only without the
So this will tell you so the left hand side in say lambda phi 4 will not tell you anything about lambda. So left hand side will only tell you about certain couplings, certain interaction which go like S squared to energy. What's special about gravity is that this includes a leading interaction of gravity.
Okay.
Doesn't happen for anything except gravity.
Like, what if you had a massive graviton or something? It's spin 2 that's important for S, right?
Yeah. Yeah, you can have some rules for massive gravity. Actually, maybe a comment on this, but it gets much more constraining for massive gravity because the longitudinal modes tend to go faster than S square. So for massive graviton, you actually get much stronger constraints.
So the longitudinal modes are like spin 1 or 0, right?
Yeah, okay. That's a good question. So what if this is a mass that's non-linear? Okay, let me just write it like this. So I remember to come up to it, and I come back to it in a few slides. Remind me if I forget.
Yes.
So the basic argument for massive, yeah. But the short answer is you can still play this game for massive gravity and it gets more constrained. So once you have this budget, once you have this constraint on the budget of energies, you can look at corrections. And the important thing is that, okay, you can write some corrections which only go like S square also exists. So in higher dimension, you have Riemann square. In 4 dimension, the first correction is Riemann cube. The first thing that actually affects it cannot be moved by equation of motion. And the important thing is that these corrections, well, you can also, they go like S square. So all corrections go at least like S square. So you can write some rules for them. And these rules involve the same unknown budget that we've bounded, but divided by higher power of the mass of these AdS states, just from dimension analysis. And then therefore, just by manipulating this equation, you get that these corrections are bounded by the mass that they come. And okay, here I've really skipped an important detail on this slide. Can manipulate the equation such that the light particles of you can like this. So the question is, when you manipulate this equation, the question is where do you have to assume positivity? And I drew the spectrum yesterday where there's a large spin mass. So there's a mass, this is higher spin mass here. So at spin 4 and higher, we allow anything here. But at spin 2 and 0, it turns out that you can allow anything here. So you have a positivity at low energies, and it's still all on the right hand side. So the right hand side includes this ether. So that tells you two nice things. So yeah, so the thing that the thing that is not obvious is that you can also assemble the equation so you don't get the denominator of the like part. So this contribution here is the mass here that contributes is really the mass of the higher spin. So spin 4 higher. So you get some relation, some quantitative relation between higher diffraction and mass of higher spins.
So it's more like maybe not understanding properly, but this higher derivative also is square. So I thought that as you is the derivative out of this converse, right? 1 square is S square.
Yes.
Just fixed by the spin.
Yeah, but you could have you could have things like Riemann 4 and so on. I mean,
there's a piece that is S squared this way.
Yeah. This Riemann square will not give things that go like a square, but the dot definitely contain things that have S cube and so on.
Oh, okay.
We definitely do. And that also makes them
So you want to just pick those pieces.
You can look at each of them separately.
And read off the coefficient consider.
Yeah.
So you can
But at some point, even that will stop, right?
That
will not
no
be
S.
No S squared.
But you might always have, like, you could have a t to the n,
yeah.
S squared t to the n minus.
Yeah, there's always so many couplings that contribute to the S square.
But the last slide, the lambda smaller than that, that should be like, is it like a general trend for all of the higher like dots, like higher derivative couplings or?
Yeah, exactly. So you get similar statements for all the other ones. So let me exemplify some of the statements we get. So in D-board 5 flat space, you get this coefficient of a bound on Riemann square. Okay, this is the bound that was conjectured by CEMZ that I quoted yesterday. But here we get an actual number. So that's a new thing. You get a sharp number. It sounds. And if you translate this, this is a 3 graviton interaction. So if you translate it in AdS 5 CFT before language, you give you a bound stress tensor 3-point function. the bound about central charges. It was known before that A minus C over C was bounded in some finite range. But now with the bound is the range shrink with the higher spin dimension thing. So if you have an holographic theory, the right hand side is a very small number. It's very bound to 0.
And how did you, the positivity seemed to give you a bound which was like a less than. How did you get the other side bound?
So the two-sided ones?
Yes.
Yeah, great question. So it's actually very similar to the way this worked yesterday for the scalar case. So once you have this Gauss-Bonnet coupling, one thing it does is that you have
Different polarization.
yeah, you can also do it without using many polarization arguments, like quite distinct from theirs. So we have something like this with and something like this. The claim is you can integrate this against positive wave packets that gives you either sign. Okay.
Excellent.
Finally, the statement of the CFT pole is like any n in capital N, n is equal to 4 over n plus something. This condition just has to be sense.
Well, yeah, the sort of funny thing, yeah. So if you have n equals first symmetry, A equals C is just a consequence of the alpha.
Okay.
But this shows that somehow if you have anything that has this large gap assumption, large ion spin gap, we also have this approximately C.
But not quite at any end, right? Because you not get accounted for loops.
Yeah.
So that's a large n.
So far, it's not ion spin, yeah, so far, yeah. But you can also get the sense, and you can also anticipate already that this sort of thing will bound the possible contribution of loops. Because the loops also contribute to the budget.
Yeah, you can do self-consistency.
When you play this game, you need the S4.
Low energy will spoil the effective action, right? Because
Yeah, you have to.
so how will you constrain the
So the way we analyze this when you calculate loops, so that's a different paper that we'll talk about, is that so in the F plane, you still have now the branch cut goes all the way to 0 and they run overlap, it's complicated. But we still draw this thing here.
Yeah.
We have to compute this arc. This is a 3 plus 1. So the picture we have is that we assume that we've explicitly calculated the loop. Actually, we did explicitly calculate the loop. And then you can numerically calculate this arc integral on the loop. That's how we end the loops.
I mean, conceptually, you have some low energy effective action. And then you work with that to whatever loop order.
Yeah.
And then whatever the answer is constrained.
Exactly. So this doesn't have
And therefore constrain the coefficient.
yeah. Exactly. So the important assumption is that this arc is calculable. If it's tree level, it's simpler. But the important assumption is that this is calculable.
you would have to work with some particular loop order, right? Not
Exactly.
particle cut.
Exactly. But because of this budget, when the one loop is small, you know the two loops is smaller. You can really be sure.
So you're almost weakly coupled there.
Yeah.
So
Just finite and you cannot say. Small, for example, you might see finite and one is not able to say any of that, right? If I say I have a CFT with a large gap but finite and finite central charge,
N equals 2.
then you cannot say
no, but in this case, what will happen for n equal to 2 is that this delta gap would never be large. So you can say.
what is N? N
N,
which
sorry.
N supersymmetry or
Yeah, no, the
gauge bank?
the gauge rank. Sorry, that's not.
Yeah, that's what central charge. I meant
Yeah,
the
yeah.
central charge.
Yeah, the central charge is not large, and this delta gap, the gap will never be.
Yeah, what is this result that can have why cannot have a large gap for a finite central charge?
Yeah, it's because
No, you could, right? If G was finite. If G was 1. Oh, you're right. I guess I said it.
if the flanks.
I said it wrong. I said it.
So
ADS is the same. sorry.
This
Well,
example here is
what
quite
happens
this
is-
theory is abstract thing. What is this?
So on the left hand side, what will happen is that if the remember that is the down and the ninth part of is between 0 and 2. What happens is that if the right hand side of this sum rule, if the right hand side is not small, then you have to worry about whether you need to. So basically, the content of what you get from the math is that you need new physics by the Planck scale. You cannot push the higher spin scale to go beyond the Planck scale. So if you have a situation where you study SU2 gauge theory, then you cannot push the new physics to some order of one multiple.
Is there a quantitative? So if there is some sort of a statement there for CFT that if the central charge is this much, then the gap has to be less than this.
No, we don't have a statement like this. There is a statement in Plan space by Vieira and friends. We study they try to effectively to extremize they look in a space of S matrices and look for the S matrices which push the new physics the further up you can. And we found that it's maximized by new physics in the Planck scale. Yeah. So that's Vieira and Mcgill. So let's jump and discuss loops. So as I mentioned, you can do calculation. For example, for dimension, you can put a scalar running in the loop and calculate the effect of the scalar regardless of gravitons cap. And see how it affects this sum rule. As I said, roughly speaking, it's useful to think about sum rules that are peaked at different. So at each B, you get a total budget that's required to match G Newton. And it's log for dimension, basically the force you get from. So there's a total budget that all of the states in your theory at this B need to add up. On the other hand, this is when you calculate a scalar loop, it's proportional to a different looking curve. So, and the overall normalization, the yellow curve is proportional to the number of scalars. So in terms of parametric estimates, like the gravity amplitudes is like G Newton S squared C, we had before, and then there's some G Newton square times number of fields in S times get something like this. And there's a scale at which they get similar to each other. And they get similar, that's this usual species scale, is similar when, let's say that S and T are the same order, we will. So basically, so the loops compete with 3. When this is happening.
These are massive scalars?
Yes. Yeah. Treating them as lighter than the cutoff. Otherwise, the curve gets slightly distorted, but it's qualitatively similar. And what you see is that the place where you exceed your budget is at the origin. At the smallest possible impact parameter, this is where you first exceed your budget. And the fact that you cannot exceed your budget, like the blue curve has to be the sum of everything you can calculate plus positive unknowns. So the yellow curve can never exceed the blue curve. And that gives you a bound on the number of possible scalars that you can have below any scale, any cutoff scale. And that number cannot exceed multiple and Planck square.
And can I understand the reason that you're getting the maximum constraint at B equals 0 is because effectively massive scalars give you a contact term.
Yeah. So I think I should draw up on the S dependency. It's dependence, but yeah, when you Fourier transform thing, I think it's a square times but yeah, basically the physics is that the scalar exchange thing, it's like a correlation function of stress tensor in the QFT, and the short distance behavior is controlled by dimension analysis to have a different exponent graviton exchange.
Yeah, so it's essentially a contact term in the end, right?
No, it's a 1 over B square. Yeah, dominated by the short distance, but it decayed like a power of the 1 over B square. Instead of being approximately constant. So they have different powers.
Why isn't it decaying exponentially set by the mass of the scalar?
Oh, yeah, okay. This is massive scalar. Yeah. For massive scalar, it decays exponentially. Okay. Excellent. So this phenomenon gets even worse at capital 1. Right.
And what's capital N? P times capital N.
Yeah, M is any fixed scalar. And so basically this yellow curve accounts for all the so it's basically M is an arbitrary scale. We assume that things below that you can calculate. Then I calculated NS scalars below that scale. And then above it, I don't know what happens.
It's a cutoff of some.
Yeah, exactly. So after this, exactly. And what you learn from this is that there's a statement of the species bound, which is that like, when this gets maxed out, something new must happen in the theory. This calculation of the loops must break down. And the scale at which it breaks down is this n has to be less than n times first equation. So this is what people call the species bound. So basically, as soon as the loops start to compete with the tree, you know that something else must appear. The description breaks down. You know, extrapolating wire. That's one thing you learn from this. The other thing you learn, and that's what we try to make more quantitative, is that the shape is completely wrong. Like there's no way that by adding loops and higher loops and so on, you will ever get the flat loop curve. So the new thing that happens when this gets saturated must be quantitatively different from a scalar loop. And in particular, because large impact parameters like large spin, whatever new physics appear must be richer in I spins. People talk about this low spin dominance. So matter is low spin dominated, but the UV completion of gravity cannot.
So it's one way of thinking of this, as you said, is just by doing the loops.
Yeah.
But another way is by just looking at the cut of the loops, right?
Yeah. You can look at the cut of loops, yeah. In order to calculate this arc, you actually need the loop itself.
But suppose I computed a smaller arc, and say it was massive.
Yeah. In practice, we often calculate this arc by defining it then.
Right, and then just take the cut, right? Treat this as.
But this doesn't quite work because you want to have a transverse momentum that of order m. So if you want to have t approximately minus m squared, the region where s is less than m, this region here where s is small is not a physical region. So actually in practice you just numerically evaluate.
But I was trying to understand whether it was obvious that. So you're saying that this loops gives you a contribution to Newton's constant, that is the physical side, the attractive side, right?
Yeah.
I was imagining that I could understand that from the cuts.
Yes.
Because it's another contribution, very much like your high energy contribution.
Yeah, I understand what you mean. It's not obvious that it came out positive.
Yeah.
And the way we calculated it was not obvious.
Okay, thanks.
So after seeing this plot, what we're trying to do is to quantify what is the I spin content, not only of loops, but of UV completion, known UV completion of the graph. So I think we came up with a very simple way of quantifying I spin content, which is that you fix some spin or representation of this V, and I guess it's V minus 1. And then you integrate the spectral density, which we said is between 0 and 2, over S, and there's a natural moment you can take it as the units of G Newton. So we expect that this integral, if you go to infinity, will give you something that's order G Newton. And for example, that large spin, you can trust the iconal approximation, large impact parameter. We actually precise expectation for what its closure integral will give you. And so then we can think of so not only does this should give a Newton, G Newton, but it's actually a very precise multiple of G Newton that you expect. So this ratio of integrated spectral density over the iconal distribution, the iconal model, gives you a very natural normalization of the budget that you expect to go from 0 to 1, and you go from low energy to high energy. So it's a very natural way of quantifying how much high spin content you've added up to an energy S. So we can plot this, and so we did this for 10-dimensional maximal supersymmetry. And there's actually few different models we can do. One of them just simple iconal resummation of the exchange that gives by definition this exactly ratio that's exactly constant. We can do this for string theory, the also Shapiro amplitude, and it's a curve that's almost the same.
So these curves are saying that known effects account for everything.
These are different models. So these three different models at the top, you see they're very similar.
Yes. And they're saying that the cuts from the known high energy behavior are saturating the Newton's constant.
Yeah, I mean, exactly. So in the thing that we know UV complete gravity, you do saturate this G Newton spin by spin.
But including the iconal, which was
Well, you have one or the other. So the way it actually works in string theory is depending on which spin you look at.
I see.
The icon it will transition from one to the other.
I see.
But you can use either model and they work.
Okay. We don't need to know much about it.
No. So amazing. But actually, so in string theory, actually, you can ask it. It was a nice paper by Svodov and Eric. They ask at which energy scale is it saturated. So if you do it for the iconal model, at large, so if you do it for Shapiro, at large spin, it actually takes an exponentially small energy, exponentially large energy before you saturate. So there's a transition between when it's actually the blue curve that's working to the yellow curve that's working. But the effect is so similar that you know. There's also one other situation we could plot. So I just discussed a few minutes ago this study by and Al on the theory which maximizes the which pushes the physics all the way up to the Planck scale. So they do this using a so-called primal bootstrap amplitude, which actually give you an amplitude. So they have like a formula for an amplitude that is supposed to have strongly coupled physics at the Planck scale. And we plot they have the partial weights of these amplitudes, so they send them to us by email and then plotted them, and it's exactly the flat curve.
Where did this amplitude come from?
So technically, what they do is that they send these to graph. At low energy, you have G Newton over you have some structure. Okay, then you put that assembly. So you have a coefficient of Riemann form. The low energy extension of Suzy. And they find they look in the space of 2 to 2s matrices, the one that minimize the Riemann form coupling.
This is like this Viera.
Yeah, exactly. So by minimizing the Riemann form coupling, you're pushing the UV completion to the highest possible, which is the Planck scale. So that's a model of where the string scale is the Planck scale.
Yeah.
That's all so we have one model and do there, and exactly the beautiful plan. On the other end, the things you can calculate, like the supergraviton loop.
So it's a little above 1, right? Even at large J.
Yeah, it doesn't have to go to exactly 1, because it's not an exact sum rule, because the exact sum rule are at fixed B.
Yeah, but large J is like B.
Yeah, it's kind of morally, they sort of morally have to go to number close to 1, but it's not the theorem that they have to go to 1.
That's the one. 1 is the budget, right? Otherwise,
Yeah, but it's not sharp budget in fixed J. So this is more like a qualitative normalization to guide the eye.
And when you say iconal model, you just mean like summing ladder diagrams of just the gravitons.
Exactly. And it's even simpler than that. You say that S is function of S and V is X of I times S. Yeah, phrase exponential trial times. And the other thing you see is that the things we can calculate from field theory techniques like the massive supergraph and the loop, are completely different. This is a log scale. They completely fail at getting anywhere close to the budget at large space.
So if I take S, on this curve I've got J and where is it?
it's infinity.
S is infinite. What?
Yeah, S infinity exactly. So this is total budget integrated over energies.
Okay.
So that's a function of spin. So basically, it decays very fast as a function of spin.
So J is the partial wave.
Yeah.
And S equals infinity at fixed J. B is
This is integrated budget, but importantly, it's integrated. It's not a partial wave. This is integrated partial wave.
int. I think. Sorry, a very stupid question. I would have thought that if I fix J and I take S large, then B is going to 0.
Yeah.
And that's at some point black holes dominate, right? Because
Yeah, but at this point in the denominator, you have a huge power downstairs.
so that is not important.
Yeah.
I see.
Yeah, black holes are surprisingly unimportant.
So large J could be thought of as large impact value.
At least for whatever it is. Yeah.
Like, should I provide selection be rose coupling? So should this equal expression of those graph for graphs also coupling? So this is two of the models. What we see is it just an angular? They contain the angular slot or
I
mean what you know what?
Yeah, I mean, there will be some, as very large spin, it's very natural to expect that the physics would be that. In theory. That's not your comment. But
Yes, so in a way, the fact that all of those coefficients agree.
Yeah.
Is that means all of them have to contain angular.
yeah, but actually, but the thing that's surprising is this is 3-level velocity without any resonation. So, yeah. So, but in a full string theory, it will smoothly go from 3-level to resonation. But both will give you, even accounting for this transition, it will still give you a flat curve.
So it will be 3-level at small j and resummation at large j.
Yeah. So there'll be some transition somewhere.
Well, sorry, mirror solution, if I did the iconization, that's formally, then also is it the same behavior? Large J.
It will be dominated by gravity exchange. It's large j.
Okay. So this part convinces us, okay, there's really a quantitative difference between things you can calculate with field theory and the completion. So we're trying to quantify this more, and another way to quantify it, now as we look at the function of, so this is the S.
It's sort of disappointing, right? I mean, all this deep stuff about black holes and so on is not showing up at all in your graphs.
No.
Okay.
I actually didn't understand that one. Why do black holes not show up in this? Like, what was that argument given?
Yeah, okay. Okay, let me show, there's a very simple thing. You see, it's about the fact that the S is 1 plus IM.
Yeah.
Okay, and the thing we're integrating is that, but with the black hole, this goes to 0. Black hole is completely absorbent, so there's no transition. That means that n is approximately equal to minus 1. So the imaginary part of n is. Now, then you contrast two models. In one model, let's say I fix on B, and I look at function of energy. This can be fixed T, and we're going to plot so imaginary part of n and E divided by say S or some big power of S. So in general, this vanish, and then there's some peak. And if you take the iconal model, okay, let me draw the case where you get something like this, and because of the extreme, you get something like that. So for black hole physics, you get the integral of a curve that looks like this. On the other hand, if you take the iconal model, you have rapid oscillations around. So that's my own. On the other one, here you get 1 plus cos. For iconal. If you put iconal physics, instead of being 1, you have 1 plus a cosine. That's rapidly oscillatory, and you have a curve that instead looks like this. But the oscillations are centered around 1. And if you ask yourself, what's the difference between the area under that curve and that other curve? There's no difference.
Nice.
But just seen from above, what you're saying is that even though black holes are very absorbent and so have a large imaginary part, because you're dividing by a large power of S.
Yeah.
That part never really contributes.
Yeah. No, but also the fact that the absorbent almost doesn't matter because there's no difference between the average is same for something that's absorbent or something
And
that's
something is also
something that's very elastic but oscillating.
Yeah. So right.
So there's really is two mechanisms.
Yeah, perfect. So both are absorbent in some sense,
Yeah.
and high energies just don't contribute.
Which is also bilateral. So yeah, this is surprisingly insensitive to details of what happens.
Could you devise some rule that is tuned so that it goes to very high energy? Some UV quantity that is not, these small coefficients, but something more complicated that gets its contribution deep from the deep. Because in a way, that's what we're really interested in.
I think one, I guess there's one basic point here also that's relevant about this plot is that if you really want to see that the amplitude is small in the UV, you really have to have excellent control over your energy. Because if you take the completely elastic amplitude that's iconal and you smear it over some window of energy, it will look absorptive just like the black hole. The oscillation is average out. So to actually see that, people often say that the amplitude, the S goes like e to the scanning amplitude goes like e to the minus XDA, there's a few things like this. But to actually see this behavior and distinguish it from the iconal, you need to have a very fixed energy. Otherwise,
Is a very rough way to say this, like looking for black hole physics in 2-2 scattering is a bad idea. Like generically,
it's
you
a
would
terrible
expect
idea.
that, like simple evaporation will give you like many quanta and you need to
Exactly.
something.
You couldn't have said it better. Okay. Great. So something else we can do is instead of putting spin on the axis, we can put the energy S. And for example, you can look at 10D algebra. One thing we can do is you can take the ratio of one spin to the next. And look at it as a function of S. And what you find is that it's always monotonic. I'll have a deep explanation why. And it grows. Eventually it saturates because the curve is flat. And so we take these adjacent spin ratios. And spin 6 over spin 4, spin 8 over spin 6. Eventually they saturate to another one number. But the sharp transition, when it starts from 0 to being order 1, that happens at a scale where the high spins start to high.
Yeah, so here the higher spins are contributing more.
Yeah.
Right?
Yeah.
In large energy.
Yeah, exactly. So if you imagine a model, we have the answer one plus loops. Then there'll be IR domain where the loops dominate, and this ratio is small. And then the high energy domain where you hit the string scale and the completion kicks in. So basically we can use this ratio as a handle to define where do the strings come. Where do the new physics come on. And the sort of cool thing is that you can also plot this for the other models I described. So you can have exactly two different models of we have a 10D. Then I have type 2A theory, which is some parameter space where actually you have the relevant parameter is the 11D Planck scale. And this onset will always pick up the minimum of these scales. So it picks exactly the scale where you have a UV completion of gravity kicks.
I mean, beg your pardon. What way?
Doesn't it make sense to iconalize this Grasshopper?
Not quite. This is ACE, this famous work by Zano and friend in the 90s, but I think it's, at large impact parameter, you just exponentiate, but at small impact parameter, it's more complicated. The streaky distance.
Let's say at large impact parameters.
Yeah, you can
So
just
this picture that you had in the previous slide, did that change and then would it go up?
No, it will be same.
No, the previous slide. This slide.
Yeah.
This orange line.
Yeah.
That change. You iconize it.
No.
At large impact parameter, should we expect just gravity too?
Yeah, that I don't understand why.
Because it's the only massless particle.
There are infinitely many mass particles, right?
Okay, but say we go very, very far.
Yeah, very high energy also.
No, but fixed energy.
Infinite energy, that's the infinite.
Infinite energy. Yeah, I suppose. At any fixed energy and large impact parameter, I think, right?
Yeah, like it's here, for example, right? At a high energy, it seems that we
High energy is a smaller impact parameter because you're fixing J.
no, but J is increasing. Those are increasing.
Right. But suppose we fix J and increase energy. That is decreasing impact parameter. Right? Because J is equal to B times E. You increase E.
Right. Yeah, I guess that this is very
Yeah, so this is one way we can. So the thing we like about this notion of life spin onset is that it always picks out well, checking three scenarios. So we can have new physics at the string scale, at the Planck scale, or higher dimensional Planck scale. And it always picks exactly that scale. And this is a purely so we could do this analysis in 4 dimensions. And it will just by analyzing the partial wave of graviton scattering in 4 dimensions, we will discover the Planck scale of the higher dimension. That's the result. So somehow this curve knows about exactly what is the physics. So that's one thing we like. The other thing we did in this paper is that you can ask, okay, this is a scalar loop, but what about other types of particles? Can they provide the necessarily higher spin states? We look at 2 particle states of various types of particles. So we did actually the one loop calculation for this has been done before, but we just put it all together. Scalar, fermions, vector, gravitinos, gravitons, massive KKM, so massive gravitons and so on, 2 forms, 3 forms, all the matter content we could possibly have in the low energy. That spin less than 2. And we computed the loop contributions, and now we contribute to this sum. And okay, one fun fact, we won't give you all the details, but one fun fact is that the massive spin 2 particle, like a Caron-Huot mode, as far as this species scale goes, it contributes as much as 2,000 scalars. Well, the spin really, the spin coupling is very important. So when people say just count the more species, actually like it's a weighted sum. So that's one fact. And okay, the other fun thing is that okay, as following things that were initiated partly by people here, we had all the technology to study the partial wave in D dimension with our Young tableaus and so on. So we did the partial wave decomposition with amplitude in D dimensions. And look at this. And again, we get this very qualitative difference between for different spins, how much this integrated vector density depends on the matter content. So for all the possible fields you have, it's a very qualitative, at least it's a log scale. Yeah, basically all the things you can calculate will decay very fast with spins. They're calculated in field theory, but the things that are not field theory, like string theory, they're very flat.
And where are all these numbers coming from? Like 1, 4, 6, 5, 3.
Yeah, this is a rescaling of the curve, which make them match to the spin 4 They all line up. So you see that in 10 dimension, the spin 2 particle counts like 10,000 scalars. So yeah, all possible possible things you can compute in field theory are completely qualitatively different from strings.
Whereas iconization is
Iconization
is good.
Yeah.
So basically, you're just doing the wrong thing by computing a one loop. You
Yeah.
computed the right amplitude and just take the iconal part of that. That is already
No, but
giving you more.
yeah, but there's a little bit. The problem is that there's a part of the phase space that's not covered by what you say. The problem is that the iconal amplitude that some J here only gets such a only kicks in at energies that are much bigger than
there's a region where there's still a mismatch.
There's a range of energy where the iconal only kicks in at very high energies, but you get something to fill you get a missing gap at lower energy.
But why am I not seeing that in this plot?
Yeah, this is a bit too yeah, this is just totally integrated. But it just means that the more field theory.
But here in the plot, it looks like iconization is doing well at every J. For you.
Yeah, iconizing the 3 levels graviton. One that again, it's
Some
if you integrate up to the Planck scale, you will not see ionization depth. You have to integrate up to energies are much, much higher.
And is that a problem if it's very large impact parameter?
I guess no. But yeah, so there's a bit of the question is once you start saturating the budget at some small spin, you wait forever until the next spin gets saturated. That's yeah. I find a sharp contradiction with not adding that, but it's sound like there's probably maybe issue with crossing symmetry or something. If you okay, maybe one last thought about this part of the talk. This is the part we put out the partial wave. So this is the ratio of Einstein ratios. Before I showed this ratio of spin 6 over spin 4. But in higher dimension graviton scattering, there's a bunch of young tableaus. So we can do something with 2 more boxes and compare partial waves with 2 more boxes. Yes. Take this ratio. And again, this ratio, like for matter that you can calculate, are very small, log scale. They are very flat for and something else that we noticed, which is sort of interesting. It's trivial it's trivial, but I think it's actually quite. But one part of it is trivial, which is that the only way to populate all of these representations is to have a matter content that is approximately there's all of these things here. So for example, it's very clear that if you don't have a spin 2 particle running in the loop, the sum of the representation with the weirdest possible shape, like 4-4, you never get. So there are some representations that are only populated by spin 2 running. But also, if you don't have the gravitino, you won't quite get the same ratio. So you need a spectrum that's SUSY on the average in order to get the flat curve. So yeah. So if we believe in some principle that somehow all the representations in the UV should have it should be equally represented, then you're forced to have if you have many species below your cutoff, you're forced to have a SUSY-like spectrum. I'm not saying that the mass level has to be degenerate. I'm just saying that the number of each field.
So what do you mean by these points for Virasoro-Shapiro? That's a scalar amplitude, right?
Yeah, that's Virasoro-Shapiro multiplied by this thing that people call TA. There's a very specific convection factor of gravitons.
Okay.
And then,
so it shouldn't depend on the spin so sensitively because it's just that overall.
Exactly. So it all comes from this TA structure.
Yeah.
Great. So that's the summary of that part of the talk. So in any theory of gravity, there exists this high spin on cell scale. At least that's a picture we're looking for. It determines whether gravity and QST break down or work. And we showed this we showed both directions in some examples, but there's still a number of conjectures that remain open. So one of the most basic things is that at this scale, we know that gravity gets modified, but we haven't shown that matter and everything else get modified.
So we can emphasize this must break part with
yes. Yeah, so part of this is I mean must break in the sense that none of the things you can calculate with field theory are correct.
Oh, okay. That's
the evidence for this.
On the other hand, eigenization more or less has it, right?
Yeah, but it's not at the right energy. It doesn't kick in.
Okay.
It doesn't kick it early enough.
Okay. Would be nice to make that statement precise, right?
Yeah, I agree. It's not yet precise. So that's probably one more other point to add. The other thing the second thing is a conjecture that's quite sharp. And it's a QFT statement that I think would be interesting to study. So here we did this partial wave decomposition of various loops and various one-loop models. And they are basically stress tensor correlators in QFT. Take the stress tensor correlator and you project it to various partial waves. And you ask how much I spin content you get. And what we conjecture is that if you do this in any interacting QFT, not just one loop, any interacting QFT, the result you would get should not be should not be out of range compared. So you should have similar ratios. So there should be an upper bound on the ratio that you can get in QFT. There should be an upper bound on the Einstein ratio, the stress tensor correlators, maybe QFT. That will quantitatively distinguish it from the UV completion.
Is there any evidence for it?
So, but the evidence comes from the fact that all the one loop things are phase separated from the rest.
I mean, you might, I don't know, if you add more and more loops, you might push it up. But...
Okay, that's why it's a conjecture. Okay. And the other item I think is very speculative, but I think particularly exciting, especially in light of this paper we were discussing earlier by Elvan, Edershi, and friends, that if you assume supersymmetry, you sort of have a lot of uniqueness of amplitudes. But anyway, there's this question that the scattering at very high energies, you get a soluble possible spin channels. And the question is, can you, like in this, if I go back to this curve here, the question is it possible to max out your budget in some spin representations and not the others? You probably have many light fields. Yet n is such that you max out the budget in some representations. And people have made an argument that for example, in the context of charge representations, we need to have the same number of charge, and each charge sector needs to be populated. The similar notion for spin will tell you that each spin sector should be populated. And if you assume that, that will tell you that somehow any UV completion of gravity that has, say, many species of light particles must somehow have an effectively supersymmetric spectrum. So wild conjecture.
Why? Where is symmetry?
It's the only way to be democratic. Only way to populate all the representations.
Sorry, I missed So I missed that point that the only way to populate all the representation is to supersymmetric.
Yeah, if you miss one of these particles, you will not be democratic.
Oh.
So different types of particles contribute differently to different.
But I thought the spirit of that paper or this argument, which populates the charge lattice, is that you start with some particles of some charge, and then you see that in the middle there have to be other representations, and then you take those representations, scatter them, and then in this way, add more and more particles to your theory.
Yeah. This is exactly. This doesn't tell you much about the density of each.
It's tell you about density, but I see. But it tells you, what must be.
So there's a bit of it's a very speculative thing, but the question is, you get enough. For the concrete question is, the way we can hope to imagine answering is that if you saturate your visual some representation but not the others, is that a problem with process? And there's something nice that happens basically if it's very easy to see why having a flat curve here where all representations are saturated is nice for crossing symmetry, because when you sum over all representations equally, you like if you sum projectors of all representations equally, you have like the identity operator. And the identity operator is crossing symmetry. So it's the same in our channels. But if you project into some representation in one channel, then it's a different projector in the other channels. So the only thing that really might be a tension with crossing symmetry of the UV if you don't have this.
So what does average matter content mean?
So to mean, for example, that suppose that we have large extra dimensions, like some people are speculating. I mean, some extra dimension of like a micron or something, which means that there's a tower of KK mode. And what this would mean is that it's not just KK mode of graviton, it would also be have equal number of spin 3.5 particles, spin 1, spin half, spin 0, that as dictated by the max of the spectrum. But the energy levels don't have to be exactly degenerate. It's just that the average density of them should be. So tower should be supersymmetric in some average sense.
but not weighted by the energy.
Weighted by energy. Yeah, so the density, the mass, the density of states in each type of field.
You smear.
Yeah, exactly. If you smear the energy over some windows, you should have.
But like the window can't be parametrically smaller than the lambda. Like
it's really integrated up to the
up to that point. I see.
Integrated up to the higher scale.
So we are not in tension with this at this point.
No, exactly. Our window is too small.
So, maybe, so is there a supersymmetric group structure is emerging at that? How can we see?
Yeah, we don't see any group structure, but this might be a useful way of thinking about crossing at this time scale. But I don't. It's not very clear, but if the spectrum is not degenerate, this is again a question where I just reveal my ignorance of SUSY compactification and so on. But how much supersymmetry breaking can you have if you have gravity nodes that are relatively light? And so I really don't. I can't say anything about it.
In the old days in string theory, there was this paper by Seiberg and Kutuzov that said that if you don't have a tachyon in your spectrum, then asymptotically the spectrum of string theory must become supersymmetric.
Yes. Okay, that's great. Yeah, that's what I'm like. Yes.
What was the basis for that?
So string well sheet argument. Or you let that.
Okay. That's great. I have a lot of questions. And this was the first part of the talk, so I don't know what to do now. So, I would like to just discuss this part too, because I think it's very cool, tough experiments. And then I'll probably skip the rest, but I like this part. So all of this is the first part was about things we can understand from like simple experiments in flat space. Yes. And it's very interesting to study non-AdS geometries. So for example, can we like bootstrap non-conformal, which would be dual. If they were holographic, it would be dual to some geometry that is not big. Or for example, if you have a conformal field theory that's dual to AdS, maybe you're interested in thermal states. And then you have some bug geometry that's not true.
But still asymptotically.
Still asymptotically. Yeah. So and the basic issue in actually doing that is that it just scares people to study a correlation function that the function is too many variables. So it's fun to just explore the space and see what the interesting corners are and so on. But the angle that I would take is just for fun. Like suppose someone an experimentalist actually like their lab was able to realize a holographic system. What experiments would you do to like measure the metric? See that it's a holographic system. So just this angle I would tell. How do you see the dream?
I mean, one could ask this question in CFT, but in a different state also. Like, if you want to ask it in a non-conformal.
No, we can also add this in CFT space.
Yeah.
And so we're asking you to imagine that your experimentalist friend was like able to make a 2 + 1 dimensional QFT that is holographic. What do you do with it? You're just like with a wall, like a poster. And then what will you do with it? Presumably, if someone can realize a 2 + 1 dimensional CFT, it will be made of atoms and electrons, and therefore it has some operator on this useful material that couples to our electron, the bulk electron. So there will be some coupling, interaction between some operator in the CFT that couples to electrons bulk, our electron. Times So if an experimentalist could realize this holographic system in 2 + 1 dimension, probably would have a coupling to our electrons, which means that if you throw an electron at the screen, there's a chance that it gets absorbed by the CFT. Okay. And from the viewpoint of the CFT, this is just like integrating O against some wave packets on this square. Sigma. So you send in some electron that has some wave, the wave function that's some wave packet. It will interact with the sheet. and source the CFT operator into what happens. We know exactly what happens in the CFT when we act with the local operator on the vacuum. It creates an excitation, and this is this picture by Hoffman and Mendocino that it creates a circular shell of energy that expands at the speed of light. Whatever the speed of light is. Okay. And so that's the basic thing. See? And again, the basic dictionary of holography tells you that you can think of it in two ways. You can think of it as a shell of energy propagating on CFT, or you can think of it as a particle that entered the bulk, as a point particle that's just moving away from you in the bulk, and somehow the radius of this particle maps to the size of this circle. Okay, so correspondence.
I thought you were saying that our world is the holographic world.
Yeah.
No, our world is not a holographic world. So we have a little sheet made by a lab that is coupled to our world. But then it looks like a door to a different world. So you throw the electron at it, and it's like the electron enters a different world that's behind the screen.
I see.
You've used cold atoms to manufacture ABJ.
Yeah, exactly. So you simulate the AGM with cold atom, you create a door to the world. Okay, so you send your electron, and somehow it became a new electron prime in that world. Now this picture here, so far, is just in your head. Just how do you know that there's a new reality to this bulk? Well, the simplest experiment, in my mind, you could do is you could throw in two electrons. One from here, and then it enters, and then one from here, it enters, and then it can collide.
So water at the critical point already is in a door, right?
Yeah.
To a different world.
No.
Very quantum world.
Quantum. Yeah, very quantum.
Very quantum based.
Yeah, the Ising model is very quantum. We'll see why in this. But yeah, so we see, so the basic of experiment is you imagine they scatter, and actually momentum conservation allows that one of them bounce back, the other comes out. And then it's amazing, like you just see like an electron coming out of nowhere. So that's, and you can also see there will also be light coming out, and there will also be the optical properties of it would really look like, you know, the stereography of like what's the angle that the light is coming from, and where you're looking from, will work exactly as if like it happened in the wall that's behind the sheet.
So for these energy shells, each shell is expanding, then they collide, and then something focuses, and then the electron pops out.
Yeah, in terms of the shell, it's actually look a bit of a crazy picture because the shell just keep expanding. And then you get another electron out that has nothing to do with the shells.
Oh, you mean the stress? But when the electron comes nearer to the boundary, isn't there a bit of the stress tensor that also localizes that?
Yeah. No, so. Well, yeah, it would be a new, but it's not related to the previous shells.
Right, but there's a new, a new lump of stuff that then
Yeah.
The previous shells should be gone somehow, right?
It's very far out.
Those particles have been scattered into different directions. So
Yeah, but it will take some time before. Yeah, I think this the red shell is this thing. But one thing, actually quite
continuously, that the shells, something happens, shells, and then shells.
the shell does not contract. But one thing I can say that I think makes this. I thought this picture made no sense at all. But one thing that's important to note is that in the energy correlation in the holographic theory are large. CT with some ranges, they are large. And that is actually important. So if you actually want to measure the energy in a one-shot experiment, you cannot. All you will see is white noise. So in a one-shot experiment, the energy density is white noise. In order to see this wave of energy coming out, you have to average many experiments because the energy in this wave is 1/n squared suppressed compared with the fluctuation of the background. So all of this is just like the current part, a little bit of current part on top of a white noise. And I think this is why it's possible that the particle comes out of something that looked like there was nothing in the middle, and it looked like there was no energy in the middle. How can the energy spontaneously appear? It's because it's just somehow part of this white noise suddenly became coherent. So that's how I think about it. But yeah, but if you didn't have this white noise to begin with, I don't think this would be possible. You can't have energy coming from nowhere.
Why is it not just?
Isn't there a shell that is shrinking as the electron comes out? Just like there was a shell when the electron goes.
If this electron is relativistic, no. The shell will not form after before.
I didn't understand. So if the electron moving that way produces a shell expanding, surely the time reverse produces a contracted shell.
Looks like a continuous process.
Those shells will so can collide.
Yeah, if a shell that has bounds from the boundary does create what you describe, but I think
I'm saying
but yeah, if the electron comes from A at the speed of light out, there's not going to be a shell that appears until the electron has hit.
You see nothing, but you see something and it's angled. At that point, there's nothing.
Yeah.
But a little bit away from it, there is.
Yeah.
And so that contracts. Okay, the electron's going to hit. So it's just let's time reverse you had an electron going from outside to inside and it kept going. So just say there was one electron, not two. That you said produced the shell that expanded. Now let me look at that same solution time reversed. If the electron was coming back out, it would be a shell contracting. So now in your colliding experiment, one of the things that's happening is the electron's coming back out. So it should have this contracting shell.
I think time reversal the symmetry is perhaps broken by the initial state of the radiation. Yeah, we'd have to discuss, but I'm not sure. I'm not sure it's actually preserved. But
okay.
So this is a bit like looking at the radiation around a particle. When you start with initial conditions that don't have the radiation. Anyway, I'm just mumbling, but I'm not sure this argument. Okay, that's a basic tough experiment I want to study. I think it would be amazing to see like literally outdoors on the notable practice. What I feel is really amazing. What I just described is how to use this type of experiments to like measure the bottom.
So this is possible only for a Gaussian, only for the wave packets.
Only for
wave packets.
Yeah, it's going to be important that we have wave packets. So let me skip.
What will happen if we have stationary?
If you have
Stationary.
yeah, then a bit too spread out to give you interesting information. Let me describe a few error extremes that people have looked at. One way you can try to probe local physics in the bulk. That's not quite wave packets. The other limit, you should have a position space. Thing with fixed positions. People have discussed this. For example, if you in DS4 as your bulk, if you take a bunch of points at the boundary and you insert local operators at these points, each insertion would create a spherical wave of energy into the bulk, the speed of light. And then when these shell intersect, you get some intersect signal. But actually, so if you have AdS4, you need 4 points to uniquely specify bulk point. However, in order to actually see that something is happening at that point, you need a 5th point to that. Okay, so people talk about these bulk point signals. If you had 5 points that happen to be in the past and future like one of a common. You get a signal when they are approached. At the basic level, there's a sociological problem with this picture, which is that you tell people they have to do tough experiments with 5-point functions. They run and go home. Nobody works on this.
So can you say why the 5th point was needed? I missed that.
Yeah. So basically, the 5th point here is needed to see how much you're approaching this configuration. Because there's let me see. If you just have 4 points, you single out one bulk point.
Yeah.
But then you vary your point and you're just singling out a different bulk point. So your signal, there's nothing special happens. In order to see that.
The bulk point is a very specific configuration of 4 points, right?
No, you need one
on the other sheet and so on.
Yeah, but you need one more. Okay, if you want to localize to a point, you need one more than the space dimension. Otherwise, there would be a contribution from some sub-manifold. If you have 4 points as equal as bar, there will be some contribution from sub-manifold.
We want the precise.
Yeah, exactly.
And how many you need will depend on which dimension.
Yeah, exactly. It's always one more than the dimension of the bulk. Yeah, that really is sharply identifies something as well.
It's just how many. You've got intersection of light cones.
Exactly.
Okay.
But it's very clear that you can do better than that if the goal is to measure the properties of the body. And actually, this was discussed in early on, is that if you put directional wave packets, then you're shooting from here in this particular direction. Then, so basically you have a light ray coming from this point. If you have a light ray coming from this point, it's very easy to specify another point. So if you take a light ray here, and then intersect it with the pulse on the other one, this will single out one point. And then I can look at it and see that coming out. In fact, in general, it's over constrained. If you have two light rays, they will almost always miss unless I tune them. Which is good, so that means you can tune and look for a bump. In physics, we love bumps. So great. So it's sort of tough experiments I want to have going. So it's very useful to have wave packets.
So it's like you've got a laser and you're shining in a particular direction.
Yeah, exactly.
And for that you need a wave.
Exactly. But I don't want to put all the way of plane wave. We use plane waves to do the calculation, but then we'll superpose plane waves so that they get localized to do satellite wave, which is the easiest joke.
And you want diffraction not to be important. So you want your energy to be large compared to 1 over the size of your.
Yeah, exactly. Yeah. So there's some optical, a lot of these measurements will be limited by optics.
So where's the fifth point on the picture?
Sorry?
Where's the fifth point on the picture?
The fixed point?
The
fifth point? Yeah, on the right there was this 5 point, but in what we do is be 4 points. When you scatter these wave packets, you don't need to study more than.
You see, the local thing is the waves are going out in every direction.
Yeah.
So then they can intersect on some higher.
Yeah.
Here you're focusing. Yeah. So generally they'll miss, but if they hit at one. Right. So you can get away with it.
Yeah, the 5th point is needed to have something you can tune to see it bomb.
Oh, so there you're not exactly scattering, like they're just focusing.
Exactly.
This is just another technique.
Those are light bulbs. These are lasers.
Right. Yeah. The lasers are better than bulbs. Okay, the basic geometry is the following. So given any bulb point, it has a future like cone that intersects the boundary at some surface, or hyperboloid. That's basically hyperboloid. And the pass like cone. So the pass and future like cone, the intersection of the pass and future like cone of the bulb point with the boundary are the primary things that matter in this thing. And the idea is that starting from any point on this pass like cone, we can focus, we can access this point, and then single will come out. We're going to be scattering massless particles in the bulk. So yeah, it's been known with nice work showing that just from the shape, if you know the family of this, so you scan over the bulk point, you get the family of the hyperboloids, and there's an algorithm that I'll review later fully that tells you how to extract the bulk conformal metric from this data. So you know this family of curve.
Yeah. Sorry, I didn't accept family of what curves?
If you know the family of these hyperboloids.
Which
future light cone? So yeah.
From future light cones from
exactly. Yeah. So you take a future light cone for various bulk points.
Particular.
That gives you a family of curves. From this family, you can recover what the bulk metric was.
Sorry, from a given bulk point, there will be 2 curves.
Yeah, 2 curves. You just need just one, but yeah, 2 curves. Yeah.
2 curves.
One
I just
pass
need
and
one.
future. Yeah.
Okay, I just need one. So basically, just a foliation, I guess, of your boundary.
Yeah.
Into codimension 1 space-like slices.
Yeah, but it's not quite a foliation because you have more than the 1 parameter family of bulk points X. So if you vary X in different directions, this will deform in different ways.
And there is not even a discrete ambiguity, I say. It's completely one-to-one map.
Yeah.
Not
It's local. It's local measurement. It's actually local measurement of the metric.
I thought if you know the hyperbola, you did a
You need
not always the hyperbolic will be bad, right?
what? Sorry.
I mean, I can draw a shape on my boundary which is not coming from
Which is not any point.
That's not 1-to-1 in that sense.
Yeah. But
So in what sense?
1-to-1 in the sorry, maybe 1-to-many. Is that one curve, one shape cannot correspond more than 1 point.
We're not going to be drawing random shapes. We're going to draw specifically the shape which come out from this part of the light.
Simple question. What is cross-section 12% weight package? So the kind of points is there just in the boundary coordinates versus variables.
Yes. Yeah. So I come to this in a few minutes. Like how do we actually do the focusing? It will be surprisingly simple. But then you just explain. So this bulk point physics is like a long story. So So we added two ingredients. One of them is to study these wave packets in any geometry, and I'll explain how they focus. And the other ingredients we needed to do, which is in the previous studies, we needed somehow, not so that this picture work, we did somehow to be able to access the bottom point from every direction. So if the previous, if you do something like a vacuum correlation function, you're throwing particles in, but in the experiment that I described at the beginning, you got one electron out, but the other just kept going deeper and deeper and further away, you don't recover it. So we also need to discuss situations where you don't recover it. That means you have to trace out over some final states and call it inclusive. So we accept that there's some particles we don't see. We just try to get information from the one we get back. Okay. And in fact, for example, the previous stuff experiment that people describe in this context, we never image a point that's inside the photon sphere of a black hole. Because if you try to have a collision, if you throw in particles that collide inside the photon sphere, there's always going to be a conservation of radial momentum. There's always going to be one particle that falls in, and you don't get it. So it's very important to trace over that particle you don't recover. Then we will be able to image close to a planet.
And outside the photon sphere, it's possible to get both back.
Yeah, but yeah. It depends on the detail. Actually, the question of which point you can get back or not is a very complicated question that we completely avoid by tracing over the things we don't get back.
Not intuitive that two guys are falling and then both come back.
No, it's very unlikely. Yeah, I agree. But it's very hard to really trace the boundary of.
I suppose if you've got a feature, if you've got a star there, they can bounce off.
Right. So maybe in the interest of time, I will discuss it. But okay, basically we added this idea, and this idea basically eventually means that you have to consider certain functions that are not time ordered. Okay, so you can look at this, but yeah, this somehow picture of the basic picture is exactly the tough experiment I described at the beginning. You send in two particles, they scatter, and then one of them you recover, and the other you just overlap with with something you add in the initial state, and which eventually looks like. So it's part of the ket in the bra, sorry, and eventually you can also draw a picture where you glue the bra and the ket at some future time slice. So you can draw a picture like this where you have a scattering event, and then the particles you don't recover, you effectively overlap.
Sorry, Simon, if I don't know anything about the bulk, how am I drawing these lines? Which direction am I sending signal?
Yeah.
How am I doing any of that?
Yeah, I get to that. But the basic picture is that, okay, from the boundary, what you can do is you can assume the shooting angles.
Yes.
And then ask if you see anything coming back.
Okay.
Most of the time you will miss.
Yeah.
But then when you have a hit, you get information.
Yeah.
And then once you have a hit, you basically measure the curve. Now you can move your
points, right? I'll get hit everywhere, basically. No, not everywhere, not everywhere.
No, there'll be a single point where two light rays intersect.
No, but where am my detectors are placed? Where should I place the detector?
Yeah, exactly. You need something that's more like a photo camera here. That records hits at all points. So you need to be able to measure the photon coming back at different places to get the curve.
Initially, we had one CFT boundary on which we are getting electron state.
Yeah.
So which is the other CFT boundary? How is it?
That's what I understand. Yeah, we only have one CFT boundary. But I don't think I understand.
But it's the same boundary, just a later.
Okay, yeah, exactly. These are all the same boundary. Oh, thanks. Yeah. These are all the same boundaries.
Yes, even I don't understand about the O one. So I think we are considering the scattering of O1 dagger and gamma 2, right?
Yeah. Yeah, the measurement maybe it's maybe not scaled. This is you can do more complicated measurement at the higher point function that are like more physically intuitive. But the simplest measurement that is actually modeled by a 4-point function is like you throw an object, you send light on it, then you recover the light. But the 4-point function actually you measure the light coherently. So you measure like the expectation of the electric field, so you measure the light with the phase.
Mm-hmm.
If you want to have something like the photon number, not just the photon amplitude, it should be more complicated higher point function. So this is measuring like the reflected, so it's basically measuring the interference between the reflected light and the light that it did not send. So it's kind of an interference measurement. That's why it's not the same thing happening in the prime. But this is just for technical simplicity to study a 4-point function as opposed to higher point functions. So what we came up is the new thing we've added is a WKB description of this type. It's not a bulk calculation. So yeah, we assume that we have some bulk state that is due to some classical geometry in a simple PDS. So background. And then we add particles on top of this background. They follow different trajectories. And we're going to neglect long-range interaction between these particles. And therefore, we assume that they all interact with each other in some locally flat region above. Therefore, we can, the correlation function will be proportional to some bulk carrying amplitude times all this propagation of things. That's the framework. So our wave packets are just simple Gaussians, as I mentioned. So there was a question about how we actually focus. But we come back to that. So we act on whatever state we have with the Gaussian operator. This creates some state with some energy. And then the picture is the following. We have to calculate the boundary to bulk propagator to figure out what's the wave function of the bulk. And we assume that most of the bulk will have geometric optics, so it follows a geodesic. Except near the boundary, there's a region where it has to tunnel through. For that region, we use AdS, exact AdS. So I'll calculate this bulk wave function and see the focusing. So the basic point is that in principle, you have to solve some wave equation in the bulk. It's equivalent to computing a single particle path integral, three-wave equation. And this quantum mechanics formulation is useful to understand geometric optics. So here's the so start with an action for a point particle, written in a form that has a smooth massless limit. So there's usual mass times 4 per time thing, mass with an einbein, nice massless limit. And then the basic information is the wave. But the thing that tells you the wave function, the amplitude propagates from one point to the other is this on-shell action. That's the Hamilton-Jacobi function of both endpoints. And the variation of this function with respect to endpoint basically defines the momentum. And this momentum happens to match with the Noether chart if you have translation, but it has nothing to do with it. Just the canonical conjugate. And this momentum, now comes the point, this momentum satisfies the equation of motion. That's a Maxwell condition in the bulk. So basically, the way we actually set it up in practice is that you fix the boundary, you fix the component of the momentum along the boundary, and then the momentum in the bulk is set by the Maxwell condition. So that's how you decide the initial condition of the bulk. Okay, one funny thing, if you ever talk about the Hamilton-Jacobi function for massless particles, it's actually very confusing. So what you're supposed to do, right, is draw 2 points and find a classical path that goes from 1 to 2. But if you have a massless particle, this only exists if 1 and 2 are not separated from each other. And when it exists, the action is identically 0. So the Hamilton-Jacobi function for massless particle is a function that is that is ill-defined almost everywhere, and is 0 where it's defined.
So the information is only in where it's 0.
Yeah, so it's not very useful. However, the Legend transform is a natural way to define its Legend transform, so in Hamilton-Jacobi formalism, you can fix either momentum or position at the endpoints. And the version where you fix the momentum at the boundary and the position in the bulk is very nice and useful. So that's the right way to think about massless geodesics. And that function, the procedure is I draw it on the next slide. So you draw a bulk point, and you find the geodesics the null geodesic that emanates from X and ends at the boundary with a certain momentum. We fix the bulk point X and the boundary momentum. Let's give you a function S of P of X. And the phase on this is not 0, there's P dot X distribution from the Legend transform, so it's a non-trivial function. The derivative of this function with respect to the boundary momentum gives you the boundary position we get. The shape of the hyperbola is completely contained in this function. And also, if you take a derivative with respect to the bulk position, you get the bulk momentum. So everything you could ever need to know about the optics of the bulk is contained in this function. Boundary momentum and volume.
Is there any relation between bulk momentum and quantum momentum?
If you have translation environments, they will have the same spatial components. Same, but in general, you have to solve the geodesic equation to relate them. They're not simply related.
This quantity is like a WKB solution of a Klein-Gordon equation. Right?
Yeah, exactly. So in the final answer for the bulk wave packet, so there's this classical phase that I was talking about, controlled by the momentum and the boundary and the position point. There's a one-up determinant, which nicely in quantum mechanics is entirely controlled by the second derivative of this function. So you don't need to actually compute anything else. And there's a constant here, which comes from this tunneling part, which we calculate from MD. It's the only place where we use that business.
And you're at high energy, so tunnels over only very short distance.
Yeah,
that's
exactly.
Not very
If delta is small, it's exactly. Well, this gives you some delta dependence of these things. Okay, and then okay, we'll skip this. So basically, you do this for every one of these paths, and then in the middle, what you have is basically if you start with the Gaussian packet and the bulk at the boundary, sorry, you evolve it along this geodesic and give you some Gaussian in the bulk. And then we do Gaussian scattering in flat space. Right. So we get a formula that somehow factorize this operator product in terms of bulk functions. You could do this for various time ordering functions and so on. But yeah. The operator in the future map to out, the operators in the past map to in, and the operator ordering is preserved. So yeah, very mumbling things that are not principle, but there's a you can do this for this inclusive sort of. It's fine.
So I've been missing the point here somehow. So if I'm totally agnostic, let's say I only know that it's dual some holographic state. Right? There's a geometry. I don't know what that geometry is.
Yeah.
What should I do?
Yeah. So what you would do is you start from 2 points in the boundary.
Just random
2 points.
Yes.
Then shoot at random angles
Yes.
until they hit. And you know that they will hit because you can record a reflected signal.
And that I put cameras everywhere.
Yeah. Yeah. And here, for example, here I show what I plot here is the magnitude of the reflected signal when they hit. And you get a curve like this. And then once you found a hit, then you can move this point a little bit. And then this curve will deform a little bit. That way you can generate a family of curves.
So I can draw this bottom curve as well as the top curve.
Exactly. And you can draw these curves you can also draw these curves for different x.
Yeah.
So you can find these families of curves by this.
Is there any consistency condition that these curves should satisfy? So that
A lot.
Huh?
There's a lot of consistency conditions.
So that I know that my geometry is a geometry and nothing weird happening.
Exactly. This is vastly over constrained.
Yeah, imagine.
Yeah.
But one can write those down.
Some of these constraints. Yeah.
Okay.
So yeah.
And this is like an in principle thing that you can reconstruct the geometry from this, or there's like.
I will give you the concrete recipe. I guess I will try to wrap up in a few minutes. Yeah. So okay. So here's the sort of thing you get in the holographic theory. You get some like this. The question came up is okay. What about you do it in 3 for boiling water? and there. Yeah, I want to start the calculation of it, but the essential thing that determines the width, there are 2 things that determine the width of these things. One of them is the size of your wave packets and all the optics. So even if you have you try to make your wave packets too narrow in position, maybe they will have too much uncertainty in momentum and it would spread.
To infinity. So you can make that very small, right?
Yeah. But so the thing that appears in the bulk is some carrying out to the nth. But the basic issue is that if S and T are both large, and for example in string theory, this would go like e to the minus up prime of f something. So the issue is that if you make your energies too large, your amplitude will get small. And also strongly frequency dependent, so you don't get a signal. So this experiment works best if you keep your bulk energies below the string scale. Otherwise, you lose your thing. And so if you try to do this in 3D analyzing, you have to use energies that are very low. The scattering amplitude, we try to have some estimates in the previous paper, but basically you have to keep the energy so low that what you will see instead of seeing this nice hyperbola is that you will see this fat X. And this is quantitatively different because the thing that is spectacular about this hyperbola, this is time and space. The thing that's spectacular about this hyperbola is that the future lepton of a bulk point give you a pulse that arrives at the bound, space-like separated points simultaneously. So that's why you interpret it as coming from the bulk of the boundary. But if all you see is just like fat X, you're just seeing boundary physics and you need the bulk to explain it.
The X will it correspond to just like a wavefront that just collided and just
Exactly, all happening on the boundary. Yeah. So essentially you can define the holographic theory as one in which this curve is sharp.
Oh, wait, sorry, you're saying the entire, even though it's not sharp, the whole feature can be explained from boundary? Just a causal.
So in the theory like I'm saying, the curve would be so not sharp that it can be explained from the boundary. But this curve cannot be explained from the boundary because you can tell that it gets flat. If you get like a fat X, then you can explain it from the boundary.
Sorry, repeat your question. You're getting a curve around a point because you're not looking at one particle.
Yeah, this X and Y here are the position of all three.
Oh, yes, a bit. If both particles came out, then they would come out at particular locations. Oh no, there'll still be any space.
Yeah, you need many experiments to make
That's
that.
good, right?
You need to repeat the curve. You need to repeat the experiment.
Yeah, the light will come out everywhere, right? Okay.
I mean, you could set a current state as full and record this record a big part of the curve at one.
Yeah, I think that scattering allows for many angles. Yeah.
heat maps produced by like taking a large number of different configurations and then just looking at this reflected back.
I missed this X versus this flat. Why is this so remarkable where X is not? For the sharp X, you also would have not.
So the question is, where is this signal coming? So if you see a signal that is so the boundary, what is going on here? You have nothing, and then simultaneously something comes in at two different space-like separated points. Or it's correlation at space-like separated points. So what's the dynamics that create that? It's easiest to explain if you have a bulk. Signal just came. Points. But if the signal starts from the origin and you see an X, then okay, you say, well, what's happened there?
The X you're talking about is like an overlap between H minus and H plus.
Yeah, exactly. The intersect. Yeah. So they were not exactly so here there was a lower upper modular that is not on the picture, but in the 3D I think they will merge.
Yeah.
Is this related to what you were discussing earlier that the outcoming electron is not like a wavefront which is collapsing and becoming one?
Yeah.
So that's the case. Is that the case where we should have an X?
Here we're not. Sorry, we'll discuss. Here I'm not looking at the energy momentum. I'm really just looking at the
1 point function.
I'm really looking at the electron field.
Yeah. So that is really clear because that you only see the 1 point.
That's right. Yeah. So I'm not trying to look at the energy source by it, just the field itself. But yeah, this energy still is confusing. Okay, so let me explain the recipe for reading of the metric. Surprisingly simple. I think I need to tell you a little bit about these curves. So given that once you measure these curves, you can understand basically the bulk in various ways. For example, one notion of depth you could have to a bulk point is like what's the back and forth time? Half of that is depth. So you could define that as depth. Another thing you can do to define depth is to use the stereography. Ask how much a shooting angle depends on your position. What's the difference between the angle and seeing your two eyes? And that turns out to be exactly the radius of curvature of hyperbolas. So if you look at this hyperbola, you can see that this point here, that this curve that are close to the center, you can see there's a bulk point that is close to the boundary. Because it doesn't take a lot of time to move back and forth. And also the curvature radius is very small. So if you want to like look at it from different place, you have to get like cross-eye. Okay, this large curvature means that. And as you go deeper in the bulk, the curvature gets smaller, and the time delay increases. These curves were made in a black hole, plain or black. And you can tell it was from a black hole. How do you tell? So the signature of a signature having the horizon is as you get closer and closer to the horizon, the back and forth time increases, but the distance does not increase. So you can see that what happened is that these curves just become time translated of each other and they no longer distort. When you see that, you know immediately there's a horizon. So now I'm going to make this quantitative. So how do you actually measure the bulk metric? Here's the concept. So this is the concept from Mcgill and Horowitz. Is that you look at the following. Suppose you have this family of curves, this hyperbola. This is from some points. And then you shoot from a different bulk point, you have x plus delta x. Suppose now that this comes from like some point on x. Suppose now that you take a bulk point x plus delta x that is separated from the other one along a line. Suppose you're shifting your bulk point by a null distance. Then the future dipole of these two bulk points will be tangent to each other. They're a tangent point. But because one of them is the future of the other, it will be strictly inside the other. So we have curves like this, where the tangent at one point and one is strictly in the other, inside the other. And this tells you that the second curve, the displacement between these curves is null, according to the bulk metric. So that gives you a definition of which bulk vectors are null. And once you know what bulk vectors are null, it means you know the conformal metric. Local. So how does it work? It's actually quite nice. So we can do it graphically. So you take one point here. Actually, here there's a symmetry. So this point and this point are clearly tangent if you shift the second one in time by the right amount. And so if they were at some different depth, according to whatever different depth you want, this tells you how much time shift. Just basically to give you this amount of time shift here, give you the coefficient of dt squared over dz squared of the metric.
But it doesn't give you the conformal factor, right?
Yeah, exactly. So far no. So far no. And then you take another point here, and if you want to make this curve here tangent, you have to translate it. Not just shift it in time, you have to translate it. And the relative amount of delta x and delta t here tell you the ratio of dz squared and dx squared. So just by doing two measurements like this, you read off the bulk metric around this point x. It's a very, very concrete recipe. It's very local. So this is very over-constrained. Like once you've done it at 2.x, you can do it at any other point and just check. General dimension. And in the scale factor, you can also read off from the overall normalization of the scaling amplitude that I described. So the overall amplitude of this signal tells you the scale factor. The conformal metric tells you where the signal is coming, but the normalization of the signal tells you the scale factor. So you get everything. So, and it's very over-constrained. You succeed only if a metric actually exists. So that's what we like about it. It's easier. We had some fun with some black holes and photon spheres and stuff. And we skip this. Very deep has a nice story about correlation functions, magnetic continuation probing inside black hole, doing scanning experiments beyond inside the black holes. But yeah, we just summarize it.
very similar question that puzzle that so let's say you wake up one day and you see two tracks, two bicycle tracks, right, made by front tire and the back tire. You have to figure out which way did the bike go. And there also you draw tangents and you see that if you draw tangents from one curve to the other, that lines will always be fixed, but that will not hold if you swap curves. And that will tell you which one
the bicycle was driving on.
If it doesn't, the tangent from the back wheel always intersects the front wheel's track and it's the same constant distance.
That's because when you move
steering with your front wheel. Exactly. So then you know which is front, which is back, and then you also know the direction.
Interesting.
The qualitatively. Questions? I would imagine, if the aim is to just kind of image the bulk, I would imagine entanglement type measurements would also lead you some.
Yeah, this is a good question because this is a bit orthogonal to this idea of using entanglement.
Because that also probes the bulk, right?
It does probe, but I think I will just make two comments here. So one of them is that the entanglement is hard to measure itself unless you have some kind of proxy for it. So it's hard to make it's really hard to make tough experiments that are based on entanglement. But if you assume you have it measured, you also need to assume some property of the bulk. Like for example, you need to assume the Ryu-Takagi formula. You need to know that the entanglement is related to area. You need to know something about the dynamics of the bulk in order to read off a metric from entanglement. The sort of nice thing about these signals is that if you get a sharp signal, you can self-consistently decide whether there was a metric or not. And if you get the metric, then okay, So you don't need to assume Einstein's equation in the bulk. In some sense, you experiment testing if Einstein. You can experimentally test if Einstein's equation is satisfied.
Right.
So it's a different viewpoint.
Entanglement probably is responsible for creating the bulk.
Yeah.
So somehow will tell you much deeper stuff. You're just looking at it.
Right. But I find it this is kind of a superficial thing, but I find it sort of cool that there's all this redundancy. And somehow this redundancy, it resonates with this notion that the bulk is encoding things in some efficient code. But it is like a very pedestrian way that it's encoded, but still, and I wonder if there's a deeper connection between this redundancy and
There's a similar redundancy. There's a similar redundancy with entanglement error. Right? That if you take entanglement entropy for, let's say, one connected surface as a function of the shape, that it is minimal area in some metric.
Yes.
Will also be highly redundant. Because the number of metrics is just 5 parameter or whatever. So, 5 into 5 parameters, what number of shapes is there.
I must was different take two differences. Yes, those complement fractions and I see I get some general variations. Examples of
I think it would be nice. So in my paper and I for the bulk, I studied 4-point functions in two extremes, so holographic theories and weakly coupled theories. So at least there we could use the rigid limit to say something about. I also try to make a reasonable model for what I thought energy scattering should give in 3D Ising. So these models are there in that paper. Now for the bulk. But I think they should be studied more because it's basically studying CFTs and very Lorentzian kinematics. So we don't have a lot of good techniques to do that. It'd be nice to revisit this.
I wanted to ask a general question, which is maybe broad enough so that we can really continue over. This is more about the first couple of lectures. In the end, what you did with the CFT reproduced all the constraints that you could get just from bulk effective field theory. Okay, with some sort of disappointing, because we believe that gravity scattering amplitudes are more constrained than field theory scattering amplitudes. Whereas the kind of constraints you get from doing just bulk effective field theory, gravity it's not so different from field theory. So the extra constraints should somehow have come from the UV, I would have imagined. And field theory, we know the UV. So you might have thought that if you did that field theory stuff, you would get more than just what you get from bulk effective field theory.
Yeah.
Boundaries, yeah.
Boundaries, yeah. So in particular, perhaps we should expect that the consistent gravitational theories are somehow discrete, or then you can't do anything. Whereas in effective bulk effective field theory, you can do anything. So is there any hint of that coming from using? So that's where you might have thought that using AdS CFT would be better than doing stuff about gravity which we don't understand. Is there any hint that we see something like that? That would, to me, be the most interesting one.
Yeah, we were very depressed when we realized that from the CFT bootstrap, we will not get things that are stronger than the symmetric bootstrap.
So far, presumably in the end you do.
Yeah.
But so what new element do you have to put in?
I'm not sure, but I think I will look at the other part of your question, which is what more can we say using the asymmetric bootstrap that is not just doing the low energy effective theory?
Okay, good.
And there I think it's really about question what happens at the UV scale. I sincerely think that if we really try to study what happens at UV scales by scattering these massive exotic spin-4 particles and so on, I really think that the space of options would shrink. Right. Just like in a 3D Ising model, these very fat exclusion plots shrink to an island when you start putting more correlation functions. So I do expect that something like this can happen.
And do you see somewhere there that gravity is different from field theory?
Yeah, I mean, I think yes. Yeah, I mean, it's at 0 4 this G Newton sum rule is very complicated, is very constraining. I think this G Newton sum rule, at least in the moral sense, it implies this notion of spin democracy that I described, that you don't need in QFT.
So suppose I took a theory of pions, something with shift symmetry, I would have a similar sum rule for the del phi to the 4.
Yeah, you have a sum rule for the first term.
Yeah, but that would be we could arrange a model where that was the first term.
Yeah.
So again,
no, but this first term is just one sum rule from 0 impact parameter scatter.
Okay.
Whereas in gravity, you get one sum rule for each impact parameter. That gives you G Newton. So you get that is morally why you would expect this democracy to hold in gravity, but not in any other theory. I see.
So you think the differences has to do with the details of the low energy effective action?
But just the fact that it starts with G Newton. I think the G Newton term, an effective action which starts with the G Newton term when you're UV completed, probably needs to have a UV that is very constrained.
Yeah. Now, the words people used to say in the old days were that gravity theories are hard to make consistent because it's hard to cut. To make a theory that's both finite, Lorentz invariant, and unitary, locally Lorentz, because any cutoff by let's say.
Yeah.
Do you see any of that? Any connect with that? Somehow a more qualitative way that gravity is special somehow.
Yeah.
It would be nice to see.
I mean, I mean, this was one of the things that maybe I can draw it. This was one of our motivations when we initially started this large end project. Is you could do the following. So this also connects to your comments about icon elements. So you scatter gravity. Suppose you have a large number of scalar fields. First thing what happens is they will come up in a loop like this. And then you can probably want to return certain energies. And actually, from a purely EFT, from the viewpoint of a purely effective theorist, you could imagine there's a consistent power counting that you can set up where you can go to the scale. So these loops are important when you hit the S, something like this. So you can resolve those things. And there's a natural EFT, there's a completely natural power counting in which no other diagrams matter at these energies. So there's a natural scale where you turn S over 1, and you turn S times 10 if 1 equal, N is over 1. So this PC scale, from a purely power counting perspective, you could have thought that this theory with the Rason self-energy makes sense.
I see. I see.
However, it violates causality.
I see. Yes. And that you just see by doing.
Yeah, exactly. You just calculate the diagram and you see the effects. And this is exactly also what happens. So yes, in principle, the loop extension gives you the correct diagonal physics at large distance. But when you hit the scale, it screws up at short distances so much that you just have to discard it. So something else that's not just a resummation of field theory must come in at short distances.
I see. Sorry, one last along these lines, and like I said, we can discuss all that, but at least at finite n, we expect the space of conformal field theories to be largely, discrete or with small number of elements.
Yeah.
I'm just rewording my question in different ways, but do you see any hint of that from doing this kind of stuff? That you change the effect of field theory in the bulk a little bit. There are so many parameters. What goes wrong?
Yeah, I don't know. Yeah, I think. I mean, this is record, right? So, am I allowed to do some crazy, wild speculations? Let's do that. I think until this week, nobody had realized how powerful supersymmetry is, especially maximal supersymmetry. So maybe there's a scenario where we start to understand how this effective supersymmetric spectrum is required on general grounds, that will be enough to get mileage from this power of supersymmetry. So, but yeah, until this week, I think nobody realized that.
What happened this week?
There was a paper by Elvan, Edershi, and someone that I'm sorry I forgot the name. Where they showed that in the context of n equals 4 Young Mills, like you would have thought that if you do a low energy expansion, you would have thought that you could add any operator like D4, F4, and so on to your action.
Yeah.
An operator that's supersymmetric to your action, and then it will work. It will maintain the supersymmetry. But what they've showed in using methods from amplitudes and consistency of 6 particograms, so what they've shown is that when you add an operator, effectively, when you add an operator like this to your action, you have to, the SUSY algebra only closes on shell.
Yes.
So you still have to check that after you've changed your equation of motion, the SUSY algebra still closes.
Yes.
And that completely collapses the number of things you can add. So basically, they show that the only option is to have the Venezian ones. You have n equals 4 SUSY and the derivative expansion.
Different compactifications of string theory wouldn't give you different.
No, same amplitude. That's all they can get.
Maybe n equals
But they need to have the maximal supersymmetry. And they also had some planar. There were some technical things like planar assumption, the assumption that you not have light states and so on. But within these very general assumptions, it was nailed to the Venezian ones.
So it's either Yang-Mills or Venezian.
Yeah. It's very strong results. I was not expecting that. Yeah.
And so what about Coulomb branch? And n equals 1 Coulomb branch?
Yeah, this would be different state without slightly massless. It just took all the states to be massless. But that's like an IR function. It's like something higher there. It's a function. It's a different state of the same theory.
Well, that's fantastic. That sounds fantastic. And this is a
Yeah, it's quite exciting.
classical tree-level exchange only.
Yes, in this regime.
That's really interesting. So it's like the CRG conjecture, but for
Yeah.
anyone.
Yeah, they prove it in one phase. Yeah. So yeah, this opens up a whole new direction.
So now we just have to double the theory for gravity.
Yeah.
Okay.
Yeah.
You get to supersymmetry.
It's a big start. If you can prove that.
All right.
Thank you so much.